A very good morning to one and all present. On Department of Biomedical Engineering, Arupadai Vid Institute of Technology, AVIT, Chennai. I welcome you all for the webinar session on advanced developments in synthesis of bio-nano crystal structures. In this regard, I would kindly request Dr. M. Ramendran, Professor and Head, Department of Biomedical Engineering, to present the welcome address.
Thank you, ma'am. Good morning, one and all present here. I welcome everyone for this wonderful talk on synthesis of bio-nano crystals. Special welcome to Dr. N. Shivakumar, and he never objects or restricts to give a talk whenever we request. So kind of him. And the topic synthesis of bio-nano crystals is a wonderful topic. It is more useful for people who work on nanoparticles for biomedical applications, biotechnology applications, or healthcare applications. So I hope this is going to give lots of idea for our students to work on some nanoparticles in future. And I hope everyone will have a wonderful session today. So transfer to you, ma'am. Have a wonderful day.
Thank you, sir. Now I request Ms. Lakshmi Sri to give you brief introductions about today's session speaker, Dr. N. Shivakumar.
Lakshmi madam.
Sir, am I audible, sir?
Yes, signal. I guess it's a problem.
Sir, am I audible, sir?
Now it's okay.
Now it is. Ma'am, we are not able to hear you, madam. Lakshmi ma'am. Lakshmi ma'am, we are not able to hear you.
Prabhakar, I think she's having some problem, network issue.
Yeah, okay, sir. Okay.
Okay, no issues, Prabhakar. Shall I give my self-introduction?
Just a minute, sir. Just a minute, sir. We'll make progress.
Yeah.
Sandhya, ma'am, can you just give the speaker introduction, ma'am? It is there in the WhatsApp.
Yes, sir.
Yeah. Sandhya, you're on mute.
Yes, sir. 1 second, I'm just opening.
Yeah, okay.
Prabhakar.
Yes, sir.
Just you give the introduction. It's okay.
Yes, sir. So, Dr. N. Shivakumar has completed.
Prabhakar, we are not able to hear.
He received various doctorate degree in 2050. Hello?
Yeah, go ahead.
Hello? Hello?
Prabha, we can hear you.
Yeah, yes, sir. Yes, sir. So Hello?
Yeah, we can hear you,
Ma'am?
Prabha.
Not here.
Prabhakar, it's fine. I can give my self-introduction. I can start. Since the time is running out of the time boundary, I can give my self-introduction. Shall I proceed, Ravindran sir?
Yes, sir. You can go ahead, sir. Yes, please.
Yeah, I'm Dr. Shivakumar. I have been completed my schooling near to Vilupuram district. And then after that, I joined as a bachelor degree scholar in Vilupuram Government Arts College. Then after that, I have joined at Presidency College to complete my postdoc PG degree. After the completion of my PG degree, I have been completed my postdoctoral research work in Madras University in the year 2015, and then after that I have joined as a postdoctoral research scholar at Anna University. And during the period, I have been published in nearly 40 research papers, and I have been received one national award for best thesis in crystal growth. Then now I am working as assistant professor in the Department of Physics at the Sairam Engineering College, Chennai. So here today, I would like to welcome you all for this session, the webinar on synthesis of bio-nano crystal structures. Welcome you all students, my dear students, and my dear faculty members and my colleagues. Okay, so I can start. My screen is visible. Is it visible to you all?
Yes, it's visible to you.
Yeah. So the today topic is advanced developments in synthesis of bio-nano crystal structure. So here completely we are going to focus on the preparation of bio-based nanocrystal structure in the case of bone studies, and for the betterment of the developing in craft materials, bone craft materials. We'll discuss one by one. Okay, so these are all some applications in relation with the biomedical. Bone screw and plates, drug delivery, and cranial plates, and dental implants, artificial heart stents, then artificial hip joints and knee joints. Clearly, we are mainly focusing on the preparation of artificial bones. It is called as hydroxyapatite. Hydroxyapatite. It is made up of calcium, hydrogen, and phosphorus component. So why we need this kind of artificial materials? Sometimes sometimes accident may happen because of aging. Some bone may get cracked, and like a dental crack, and sometimes it's artificial heart stents. So all these kind of things can be rectified by using this kind of artificial bones. But here my idea is, I have taken the accidental bone, natural bone, then I have studied all the analysis on the natural hydroxyapatite, so that we can come to know what is its actual physical characters, like what is its structure, what is its spectroscopic aspects, what is its porosity nature. So these are all the physical properties and the chemical behavior we have to identify. So based on that only we can go for the preparation of artificial bones, that is artificial hydroxyapatite materials. So here we have a ethical committee. We got the ethical clearance, so that after submission of that ethical report to the hospital, then only they can provide the bones. So this is in the age category of 40 to 50. So from age category wise, it is getting different. Structure is getting different. For the adults, it is entirely different, and for babies, it is different. But it is made up of crystals. That is a nano crystals. Okay, but it is the arrangement is different, but the structure is same. Okay, it's like a bricks. So bricks are same. Okay, but the house is different. The house shapes are entirely different. Like that. Here, these are all bricks. Okay, right. So here, this is the scale from macro to micro at the top, and here at the bottom from right to left, it is a nano to macro. That is a micro to macro. Okay, let us consider a natural bone. This is a natural bone. One can able to take two parts of the natural bone, of the side surface and as well as at the top surface. the side surface, it is called as cortical bone. This is called cortical bone, and on the top we have a cellulose bone. What is the difference of these two? These two are made up of same hydroxyapatite crystal, but structure is different. Once you taken the picture of this cellulose bone, it will be having a porosity structure. See the pores? It will be having the size around the diameter size around 200 micrometer. So this one bone structure is called a trabecula. Okay. This one bone, that is one pore structure, is called as trabecula. These are all the some terminology which is which they are using in medicinal section. Okay. Here we have a Austin. Austin means it will be having a different kinds of disc. Disc structure is called Austin. Okay. Here we have 1, 2, 3, 4 different cylindrical shaped structures. It is a stacking. It is like a stacking manner, and the bottom one having a diameter of about 100 to 200 micrometer range. It will be vary. This diameter size will get vary for different age categories. Okay. So at the bottom, I'm taking one part. That is the disc at the bottom. I'm taking the section of the one section. It is called as lamella. One can see it is having a more number of straws like straw structures, like fiber structures. Okay. Even you are taking some small portion in the trabecula, this will also be in the same. So it is understood that the entire bone is made up of lamella, but it is having a different structure, like a bone structure, and that is a cellulose bone structure is a porous nature, and a cortical bone like a half cylinder disc structure, so etc etc. So these are all different arrangements, and nature is making a very wonderful thing here. Okay, so here this lamella will be having a diameter of about 3 to 7 micrometers. So one lamina. This lamella consists of so many fibers like this. This is called collagen fiber, approximately in the range of 500 nanometer. Okay, this collagen fiber is connected through hydroxyapatite crystals. See this black color one. This black color is hydroxyapatite crystals. This is in the size of 50 nanometer. Okay, but the strands are made up of like a DNA structure having a thickness of about 1.5 nanometer. This is called tropocollagen. Okay, but our ultimate aim is it is not possible to prepare this tropocollagen. It's a very tedious process. That is why people are going for this hydroxyapatite crystal. Why? Because the size of the tropocollagen is very small, 1.5 nanometer. Just imagine, it's not possible to visualize this structure. This 1.5 nanometer is not possible. Why? Because we are having a visible range of about 350 to 700 nanometer. That is a range of visible. Okay, this is very less than. Okay, even this also 50 nanometer is also not possible to see our eye, but one can get all these kind of information through studies like TEM, HR TEM, and SIM studies and all. SIM studies, you can go up to micrometer scale. Even some the sample is very good. One can go for nano scale also, but the appropriate study is TEM. Okay, I will tell you what is TEM and SIM and all. Okay, so now you can able to understand why this part of hydroxyapatite crystals are very much important in the field of medicine. So here our ultimate aim is to form this hydroxyapatite crystal, but since this is the artificial crystals we are going to prepare, we won't have this kind of structures. Okay, all are made up of hydroxyapatite crystals. It will give more strength to the body. At the same time, we need to check its compatibility to the person. Okay, so this is I have focused only on the age category of 40 to 50. I did not go for above 70, 80 and all. Why? Because it's ethical committee not allowed to go to get the bone materials in the age category of 70 or below 20. They are not willing to give authentication. Okay. Anyway, so this is different, but this is our ultimate aim. We need to develop hydroxyapatite single crystals as a artificial bones to replace our problems like cracks, bone cracks, then hip joints like that. Okay, right. So this is the preparation part. The human bones were collected from hospitals to understand their characteristic properties on different sintering temperature. Why this kind of different temperatures are essential? When you are going for higher and higher temperature, whether the structure remains same or getting modified. This is our ultimate aim to study. So if the material is withstanding a maximum amount of temperature, then it is understood that that material can be useful for long run stability, for long life. Okay. So here I have been selected the bone materials, that is the proper bone materials without any impurity, and cut into small pieces of dimensions 10 mm, 5 mm, 5 mm. That is length, breadth, and thickness. Length, breadth, and thickness. Okay, this is in millimeter range only. Okay, now after the preparation of this, means after selecting this kind of bone pieces, we are going for sintering for 3 hours. At 250 degrees centigrade, 350 degrees centigrade, 550 and 750 degrees centigrade, and all in the furnace. This furnace, the furnace what I have used in our laboratory can withstand the maximum amount of temperature of about 1400 degrees centigrade. Before the heat treatment process, we need to sinter or dry the sample at 100 degrees centigrade at least for 20 to 24 hours to remove the dirt formation over the surface of bones. We want to get a clear pure bone, we need to heat treat at 100 degrees centigrade at least for 20 to 24 hours. Okay, then I can show you the photograph. Then after that, we have been utilized all these materials for different characterization in order to understand their physiochemical properties. Okay, see, this is the natural bone. So see the structure. It's an actual bone, natural bone. This is a natural bone. I'm talking here about the natural bone. Okay, so one can see the porous nature. We are thinking that the bones are very highly dense. We cannot have this kind of structure. No, at the outer surface only it is highly dense, but inner surface we have a porosity nature. That's what I am showing this picture to you. These are all natural hydroxyapatite, NHA, natural hydroxyapatite simple crystals. What is its chemical structure? Actually, calcium, phosphorus, hydrogen. Generally, we can call this as calcium hydroxyphosphate. This is called a hydroxyapatite crystal material. Okay, so here, what is the synthesis? Chemical synthesis. We need to take. Here, I am talking about the artificial preparation, not discussing about the natural. How to prepare artificially. But I have not done any artificial work. This is in the preliminary state. I need to compare this study with the artificial bones. So that I need to know what is this chemical reaction inside and how many water molecules may be there, will it affect or not. These are all the things we need to discuss, so that I'm showing this chemical structure to know how to prepare the hydroxyapatite materials. Okay, so this kind of artificial hydroxyapatite materials are used to make bone crafting, dental repairing part, and hip replacement section, and dental implants and bone conduction implants. So all these applications, we need to know what is its structure, what is its chemical composition, what is its spectroscopic vibration nature, what is its thermal stability, and what is its electrical conductivity, what is its thermal conductivity. So many physical parameters are there. Some of them one can able to discuss. So the preparation of natural hydroxyapatite materials are possible by chemical route. It's a very simple technique. Okay, people are using some advanced technique, but even though it is advanced, we need to cross check with this. So this kind of natural bone studies, we are only first doing, means in our team. Why? Because it is a very tedious process to get ethical authentication from the government to discuss all these bone studies. Okay, right. Here, this sample one can see at the room temperature and at 250 degrees centigrade and 350 degrees centigrade and 550 degrees centigrade. and 750 degrees centigrade. One could see the different colors in the sample. One is in first is in yellow, then it's a brown, then again it is going to be a brown and some whitish, that is a ash white, and then here the pure white. So once you reaching this part of pure white, then after that it becomes ash. So when you are reaching the temperature of about nearly 800 to 850 or 900, it is completely ash. So structure is completely getting varied. So that it is understood that the maximum stability of the material, hydroxyapatite natural bone material, is 750 degrees centigrade. Okay, right? So that it won't affect the atmosphere after the 70 degree. It will be like an ash. Okay, that's a different phenomena. We'll discuss later. Okay, so after the preparation of this kind of samples, we need to grind it. So we need to take these samples in as a powder form. See, this is the powders. The figures, adjacent figure shows the powders of this kind of hydroxyapatite materials at different temperatures. Okay, then what are all the characterization? Basic characterization one can able to understand the chemical part and then it's a physical phenomena. First one, we need to confirm the structure, which is belongs to which structure. So for that, we need to go for powder X-ray diffraction analysis. Then Fourier transform infrared spectroscopy in order to find out what is their chemical compositions and their own molecular behavior, molecular vibrations and all. Then scanning electron microscope in order to understand their morphology and porous structure. What is the porosity structure of when you are increasing the temperature? When you increase the sintering temperature, how the structure is getting varied, or whether that the diameter of the pore structure is shrinking or expanding. These are all the details we need to know. Then after that, UV visible spectroscopy in order to identify this kind of bone materials or belongs to conducting material category or insulating material category. Okay. For that, we need to go for UV visible spectroscopy, then Hall measurement. This will give all the electrical parts like resistivity, conductivity, and Hall mobility, and the magnetic resistance strength, the electrical resistance strength. So all these kind of parameters one can able to derive from the Hall measurement system. Okay, so we'll discuss one by one. So this is the very simple and basic picture to explain the diffraction studies on the materials. This is prepared only for students. Okay, how this X-rays are getting diffracted and how we are collecting the informations and what is the basic science behind the X-ray diffraction analysis. Here we have a circle. This is called a goniometer circle. The circle is called a goniometer circle. At the middle, that is at the center, we need to keep the sample. Okay, so the X-ray will be coming from the X-ray tube. This will be incident over the sample. That sample will be getting, that means the sample diffracted. The X-rays which are coming from the tube, that diffracted X-rays will be collected by the detector. Okay, if the X-ray tubes rotate in the clockwise direction with the angle of theta, this detector will rotate with the anti-clockwise direction with the angle of 2 theta. This is very important. Generally, if you are seeing this, all the powder X-ray diffraction diagram, along the x-axis it will be a 2 theta because of this detector position. And then one can able to find out the counts, the intensity count along the y-axis. That is, we have a zinc sulfide screen to detect the X-ray intensities. Okay, so this is the basic informations I want to share with you, how it is getting working. Okay, then what is one more science behind it? Generally, you might be knowing X-rays, the production of X-ray. How X-rays are produced? X-rays are developed by stopping the fast moving electron by a metal target. So the fast moving electrons are suddenly stopped by a metal target, there is some radiation that we don't know what is that radiation. So that Ranjan put as X, the symbol. X means unknown. So now we are calling this as X-ray. That's it. Okay. So fast moving electrons, when you are stopping suddenly, then there is an emission of rays called X-rays. Okay. So here we have shells, different shells. I'm coming to the atomic structure. This is centered in the nucleus. We have so many shells: K shell, L shell, M shell, and so on. Let us consider a primary electron is coming outside from the electron gun and getting incident over the nucleus at the K shell. Therefore, there is a removal of electron from the K shell. So ultimately, what will happen? There is a occupancy at the K shell. That means there is a vacancy. This vacant site will be filled up by the nearby electron which are present in the L shell. Therefore, the electron present in the higher energy state will be going to the lower energy state. Therefore, there is an emission of X-ray. See, this is called characteristic X-ray. So all the X-rays or the spectrum we are recording from the powder X-ray diffraction equipment is characteristic X-ray. What is the meaning of characteristic X-ray? This characteristic X-ray completely explains the despacing and their own reflection. Their own, that is the material. Let us consider some of the like zinc sulfide or cadmium telluride. So many materials are there. So its own characteristic application. Why? Because all the elements are related with their electronic configuration. We are naming the elements according to their electronic configuration, electronic arrangements in K shell, L shell, M shell, and so on. So this kind of electronic information can be able to understand by the emission of this X-ray. Hence, it is called as characteristic X-ray. Okay, why? Because the X-ray pattern will reveal the structure. The structure won't be same with the other materials. Cadmium telluride is getting different structure, and zinc sulfide getting different structure, zinc oxide getting different structure. This means due to what? This is due to the electronic arrangements. So this kind of information can be easily understand by this kind of equipments like studies, powder X-ray diffraction studies particularly. Okay, this is the setup. Here, this is called source. This left one is source, the right one is detector. So we need to keep the sample at the middle. See, we have a plate. Over that, we have to keep. There are two modes are possible. Either sample rotation or detector rotation. Two modes are possible. But here we have a stable state. Here sample is at stable state. Here this is the source and this is the detector. Okay, right? This is the, just I'm going to give a typical figure to understand what is this equipment scenario, or how the section will be, how it is getting equipment figure. Just I'm going to show. Okay, okay. So we have done all the X-ray diffraction studies over the materials. First one, the first figure A, that is natural bone at room temperature. One could see there are some peaks and as well as some noise. Why this? The natural hydroxyapatite at room temperature will not show its crystallinity at room temperature. Why? Because this natural hydroxyapatite bonds at room temperature will have a trace amount of sodium, chlorine, and some water molecules, which gives or which results in poor crystallinity. When you are heating that material, its original crystallinity will be present. At a 250 degrees centigrade, at 211 plane, for the 211 plane, see the 211 plane, for room temperature, the density is less. When you are increasing the temperature from 250, 350 to 750, one can see the sharp increment of intensity. That means the crystallinity is increased. It shows its better nature at the 750 degrees centigrade. This is called the crystallinity behavior of the sample. So by the way, one can be able to understand the heat treatment will play a major role in finding out its crystalline stage. That means, by the way, one can be able to understand whether the material getting their different structure or not. So up to 750 degrees centigrade, its structures remain same. Okay, all the peaks are at their own position. There is no change in its peak position. They remain same. There may be some nano strain, but it remains same. When you are going the temperature beyond 750 degrees centigrade, its structure getting changed. It becomes amorphous in nature. Why? Because at the higher treatment process, the molecules may absorb more amount of heat energy. Therefore, it's getting break. The bonds are getting break. Therefore, the entire structure will get collapsed. Then finally, it becomes ash. It's the amorphous nature. Okay. So see the wonderful behavior of the material, and that too one can able to predict or identify through this kind of studies like X-ray diffraction analysis study. So this is very important to understand their stability, thermal stability, and the structure and phase transition, etc. Okay, so this is the nature. When you are going for a higher and higher temperature, there will be the removal of trace amounts of sodium and chlorine and some of the water molecule, not entire water molecule. Why? Because this is natural hydroxyapatite contains more amount of water molecule. These water molecules are called as what we say water of crystallization. It is not possible to remove it. Actually, it is not really. It is not possible to remove. It's having a very strong binding force with the molecules. It is not possible to separate this kind of water of crystallization from the molecules. Even you are going for higher temperature, it's not possible. You can say that, sir, at 100 degrees centigrade, it must remove the water molecule. No, it's not possible. If it is ordinary water, it may evaporate. But when it is combined with the molecules, it's not possible to remove easily. Okay, right. So then these are all the comparison. This is natural bone. It shows it's a D values at 25, 31, 39, 46, 49, 67. Then these are all the hydroxyapatite materials centered at a different heating rates. 250, 350, 550, and 750. See, all the D values remains at same position. See the 25, 32, 39, 47, 49, 64, like that, 26, 32, like that. So all the positions are remains the same diffraction bracket position. So it is understood that there is no change in structure. Even we are going for temperature up to 750 degrees centigrade. Are you there? Students, are you there or sleeping? I'm only speaking here.
Students, sir, am I audible?
Yes, sir.
Sir,
Okay,
in
sir.
this regard, just sorry for interruption. I just wanted to make a statement that I'm very sorry because initially when I was able to do that welcome address, there was a lot of hiccups. And
nothing to worry. It is our students. I am willing to
I'm very
take
sorry
the
for
lecture to the students. No, it's not a matter. Can I continue?
Please, sir.
Okay. Students, please don't sleep. If you have a doubt, please ask me. That's my ultimate aim. I need to clarify your doubts.
Yeah, students, let this be an interactive session. So just ask some questions to sir, and he has a lot of knowledge in bone replacement, and he have done many researches in bone materials, and currently he is in postdoc. He has completed postdoc actually, so he has a lot of information stuffs. So if you people have any doubts in the regard of bone replacement or the composition of bones and how to test the bone samples and so on, please don't hesitate to ask. Please raise your hand and I can allow you to talk so that we can directly interact with the sir. Or if you want to put your questions in chat box, yes, it is also welcome. Please put your questions in chat box so that we'll have a discussion. So this webinar is entirely organized for you people. So you have to get benefited over it.
Okay, Prabhakar. Then what is the time limit up to?
Sir, you can take, sir, not a problem actually. If you want to
Okay,
continue,
yeah.
you can continue. Yeah.
Okay. As much as possible, I can continue. Then
Yes,
if
sir.
it is not able to continue for more than 1 hour, I can skip some of the slides. Then I can give the straight information to the students. Yeah.
Yes, sir. Yes, sir. You can proceed, sir.
Yeah. Okay. So it is understood that all the structures remains constant, and all the D spacing and HKL values or remains at the same position of bracts. It is identified that all the structures are same. There is no change in structure. Okay. I'm moving to the next one. Yeah. Then we need to cross check the lattice parameters. This lattice parameter will play a major role in order to identify their system, crystal system. This belongs to the hexagonal crystal system. For that, the A value and B value should be same, and the C value is different from the AB values. What is this ABC values? It is like a x-axis, y-axis, z-axis. Okay, ABC, and this will provide you the three-dimensional structure. Therefore, we are calling in our physics manual as ABC. If it is a mathematical term, it is x, y, z axis. Okay, then all are in the Armstrong unit range. So here the reported natural hydroxyapatite, that is a Sudarsanan and his team, they found this ABC value for the natural hydroxyapatite crystals in the year 1969. They reported the AB value as 9.4 and C value is 6.879. Okay, but here in our experiments, we have been recorded these ABC values for all the temperatures. So for all the temperatures, there is no much variations. It is also confirmed that there is no structural variation. So see, the structure is very, very important. That too, we are discussing in the angstrom level. That is particularly if you are taking into nano level, it becomes 9.42. 4, it becomes 94 point. So 94 nanometer is also very good. It is very important. We are discussing in the nanoscale. That is why nano is very, very important. Okay. So since we are discussing about the nano level, one can strongly endorse the study that the structure remains constant and there is no structural variation. The structures are getting stable. Then at the same time, we need to analyze what is crystallite size. We have a formula, Scherrer formula. By using the Scherrer formula, one can able to find out what is the crystallite size. People, all the research scholars and the fellows are thinking that the crystallite size and particle size are same. No. Crystallite size is very, very small when compared to the particle size. Crystallite size is entirely different from particle size. If you are taking one particle, if you are seeing the structure, one could find out more amount of grain boundaries. So each and every grain boundary will have a collection of crystallite size, that is internal domains. When you are increasing the temperature, the domain will grow. Can you able to imagine? Let us consider your particle in the spherical shape. Okay. When you are discussing about that structure of the particle, one can visually see through the SEM or TEM the grain boundaries. SEM is not possible. If you are going the TEM, one can see the domains, different grain boundaries. Each and every grain boundaries are made up of many crystallites. Crystallites are very, very small. When you are increasing the temperature, then only it will grow. Okay, it will get elongate. That molecules getting elongated. Therefore, the grain will grow. This is actual fundamental science. Okay, so that for natural hydroxyapatite, the crystallite size is 7.2 nanometer. When you are increasing the temperature, see, there is a extension of bond length resulting in increment of crystallite size. See, as temperature increases from 350, 250, 350, 550, and 750, there is a gradual increment. So, by the way, one can able to understand that there is an effect of temperature. Okay, but this kind of nano structural strain won't affect the crystal structure. That is important point. See, all the higher temperatures from 250 to 750, there is no structural change. But even though there is no structural change, there is some nano structural strain. You should not say that it is a structural change. It is a strain. Strained, that means slight shift. You cannot see, you cannot observe. But that is the importance of X-ray diffraction analysis. One can get this kind of information. This equipment will provide all this kind of information. It is not possible even you are going for 10. Okay, so this is the formula for finding out the crystallite size, not crystalline. That is wrong word. Remove that. It is not a particle size. Remove it. It is crystallite size. Okay, so this is the formula which I used for the calculation of crystallite size. It is in the nanometer range. Lambda is the wavelength of X-ray, what we are using. Then beta is the full width half maximum value, and theta is the angle, the degree. Okay, all these estimated crystallite size have been presented in the previous table. Then from the table, it is understood that, as we discussed, the crystallite size increases as the sintering temperature increases. Okay, so the sintering temperature also removes the unwanted impurities and water molecules. At the same time, there is a growing of grains, will result in the increment of crystallite size. Okay, then next study is the Fourier transform infrared spectroscopy. This will provide all the molecular vibrations. So, by using this kind of study, one can able to identify their molecule structure. Okay, but I want to discuss about something more relevant to the bone structure. So now I have confirmed the structure. After that, I want to discuss with you same photographs. Then after that, their electrical nature. As I am having some other work, I'm going to give some brief introductions and the results of this kind of another studies like Fourier transform infrared spectroscopy and UV visible spectroscopy. If I am speaking, it will take 3 hours or 4 hours. Okay, so you might be sleeping. You may sleep. Already you are in sleep, I think. Okay, right. Anyway, so Fourier infrared spectroscopy, transform infrared spectroscopy, TIR spectroscopy. This is the actually pictorial representation how it is getting work. Okay, but I'm not going to discuss about this. Okay, I will tell you more important than this study. This is the equipment. Okay, this is the recorded spectrum. This one is the recorded spectrum. This is the equipment. This is the sample preparation, and then how to prepare the sample and what is its surface and all. After that, only we need to keep the sample inside of this box. This equipment. We are sending the IR radiation. Then we are recording the vibrations that is present in the screen. Okay, this is the spectrum for natural hydroxyapatite. OH bond and H2O and H2O bonds from 2500 to like 4000 centimeter inverse. The wave number range, one could see the water molecules. Okay, then other carbonates, phosphate, vibrations, everything is present. So it is confirmed that it is completely hydroxyapatite material. But the calcium and all we cannot identify from this FTIR spectrum. Instead of this, we need to go for Raman spectrum, Raman analysis. Why? Because in this FTIR, that is a Fourier transform infrared spectroscopy, we have some specified range. That means 400 to 4000 centimeter. That is range. Apparatus range and IR range is this one. the case of if you are converting that into wave number range is 400 to 4000 centimeter inverse, so that it is not possible to go less than 400 centimeter inverse by using this setup. It is the higher range is that only. So that we are going for Raman spectroscopy in order to identify the elements, element vibration, calcium elements. Okay, right. Okay. Anyway, so it is understood that all the vibrations are present in the natural hydroxyapatite materials. By the way, one can able to understand there is no structural change and all the materials are present in the sample. Okay. Then here for different sintering temperature, we have been recorded the FTR spectrum. So all the peaks, see here, all the peaks are remains at their own position, so that it is identified that even you are increasing the temperature, there is no change in vibrational position. There may be some slight change, but vibrations are at the same position. But one could see the water molecules. See, even we are at the 750 degrees centigrade, we are unable to remove the water molecules. See, at 3400 degrees centigrade, sorry, 3400 centimeter inverse wave number, there is a broad band that represents that the presence of water molecules in all the samples got not getting removed. That's what I told you. These are all the molecules called water of crystallization molecules. It won't remove from the source molecule. Okay. At the same time, we need to find out splitting factor. This is very important section in order to identify whether the structure is getting more deviated from their own structure or not. Okay, splitting factor. Splitting factor for the natural hydroxyapatite is 1.9, and for the 2 degrees centigrade have been analyzed, it is nearly 2.0. So it is also providing the same statement. There is no change in structure. So all these studies are representing the structure. Structure is more important. That's what the people are more concentrating on structural analysis. See, these are all the vibration assignments for natural hydroxyapatite and for sintered materials from 250, 350, 550, and 750 degrees. So then another important use of finding the splitting factor is that whether these materials are getting crystallized or not. So there is a correlation between the powder X-ray diffraction and the Fourier transform infrared spectroscopy. In the case of powder X-ray diffraction, as I told you earlier, when you are increasing the temperature, what is happening? There is an increment of crystallinity behavior. Okay. At the same time, the same can be reconfirmed by this kind of spectroscopic studies like FTIR. See, the splitting factor is getting increased. For natural hydroxyapatite, it's 1.98. It is a 2.10, but more or less it's same. But there will be some slight increments. One can see the slight increment behavior. This kind of slight increment of splitting factor shows higher crystalline nature of the sample. So this study supports powder X-ray diffraction analysis. Yeah, this is very important. Scanning electron microscope. Yeah. Electrons from the source. These are all called as primary electrons. Electrons are coming from the grid, that is from tungsten grid. All the electrons are coming and it will be focused by so many lenses and it is focused on the sample. Okay, so the sample thickness should be around 2 micrometer. You should not have more than that. You should not have below than that. Below than this range is not possible. Why? Because this is a manual preparation. We need to get the stub. Over the stub, we need to have a carbon tape. Over the carbon tape only, we are going to put the sample. Very small pinch of sample is enough. Then we need to blow it. I'm discussing about the preparation for this kind of test. Okay, so we need to air blow it over the sample, so it will be spreading over the entire carbon tape. So the carbon tape we need to keep it in the instrument then we are going to send the electron beam over it. There are many electrons maybe coming out from the sample. Each and every electron emission will give their own characteristic properties. What are they, sir? See here, we have a balloon shape. Okay, what is this balloon shape, sir? This is the entire thickness of the sample. That is 2 micrometer. Let us consider the electrons are coming and hitting over the surface of the sample. Some electrons are getting emitted. That is this orange line. These electrons are called auger electrons. Then some of the electrons are coming out from the sample after some distance. After that is the below. The next stage is secondary electron emission. Then the electrons which are coming out from the third stage are called as characteristic X-ray. If you are having emission at the bottom of the sample, it is called photons. That is light energy. Oh, these are all possible. So many electrons are coming out. Yes, of course. Really, when you are sending an electron beam to the sample, there are more collisions will be taking place, like elastic collision, inelastic collision. These are all due to inelastic collision. If it is electron collision, the electron will be getting jumped. That is different. But here, the electrons are getting penetrated to the sample. Therefore, at different positions, there are different electrons. Auger electron, secondary electron, characteristic X-ray, photons. Light, that is ready. Okay. Then backscattered electron. This is related to the elastic collision. It won't give any information. It is simply this backscattering. But this kind of backscattering will provide the information about the elements along with the characteristic X-ray. Characteristic X-ray and backscattered electrons, all this will provide the redox spectrum, energy dispersive X-ray, redox spectrum analysis. What are all the molecules present in the sample? That are all the information one can be able to identify. But the structural, that is a morphological structure can be identified through this secondary electrons. Secondary electrons are responsible for finding out the surface morphology. That means morphology means how the structure, whether it is a circular shape or porous shape or rectangular or square, triangle, different shapes, or strands and fibers, so many. Okay. Then what is the purpose of photons? Photons means it will be having energy of E is equal to h nu. With the different energy radiation, it will show different colors. Okay, that is called coloring image. So that coloring image will show, or the colors will be related with the elements present in the material. So that is called mapping. Okay, so there are so many applications. There are so many information one can able to collect it from this scanning electron microscopy. Okay, so this is the typical diagram for understanding how the system is getting working. See, here we have an electron source. Electrons are coming from the electron gun, and we have an anode. This anode is connected to the high tension battery in order to take all the electrons through it. So all these electrons will be focused by the condenser lens to the aperture. We have different holes at the aperture. So one can able to change manually. Okay, we can change the aperture. So so that one can able to have a fine focus on this sample. Then after the aperture, it will be scanned by the scanning coil. Then we have objective lens. So there will be a fine focus. There is a single pencil line beam. We cannot say it's like a beam. It's like a 2 to 3 collection of rays. So all these rays are incident over the sample. Then the electrons are coming out. As we discussed earlier, we are going to discuss about the secondary electrons. So this secondary electron emission will provide the information about the surface morphology by the secondary electron detector. How it is there? What is the structure, sir? What you identified? I'll tell you. This is the setup. Okay, Kana? So this is the picture, images recorded from this instrument as a software through the software. Then we have a grid. See, this is the electron grid, electron gun. Okay, inside of it, we need to keep the sample here at the bottom. Here, see, this part is there, no? So we need to take it and then we need to keep it, and then you should maintain your vacuum, very high vacuum. You should not have a air molecules inside. Then it will get affected. The entire system will get spoiled. Air molecules will get easily ionized. Okay, right. Okay, right. I'm coming to the point. See here, natural hydroxyapatite. See the structure, pore structure. Okay, then at the 250, 350, 550, 750. What is the information one can able to get it from this thing? What is the use of this? See, samples, natural hydroxyapatite, a diameter. See, I am having a two cross-sectional lines. Okay, in order to find the average diameter of this porous. Here, D1, D2 value and pore diameter is 632 micrometer range. When you are increasing the temperature, its size is reduced. 612. Again, 608. At 550, 473. At 750, 395. See here, when you are increasing the temperature, the pore size getting reduced. Can you tell me, anyone, why this? Okay, I'll explain. When you are going for higher and higher temperature, the pore-like structure will shrink, will get shrink. The bonds between the atoms will get compressed. You are thinking that the bond between the atoms will get elongated so that the entire size that the pore structure will be maximum. No, it's not like here. When you increase the temperature, let us consider more. You are having more number of straws. For the straws for coconut water, while you are drinking, you will be having a straw. No, let us consider a collection of straws. Straws. Just heat up, it will get shrink. Instead of expanding, it is getting shrink. That is the nature of pore structure. When you are increasing the temperature, the pore size must reduce. That is the basic science that we have confirmed from this analysis. Okay, so at very higher temperature, the entire size will get completely shrink. Then it will be like a ash, like particles. We cannot use it. Okay, so this is very important analysis to identify the effect of temperature, whether the diameter is getting shrinking or expanding and all. So the details are very important in science and the preparation of bone. Then, so whatever I have discussed, that only I have given here. The same photograph shows no difference in morphological structure. All are pore size, but the pore size of this materials are closely related with the material strength. That is very important. Larger the pore size shows reduced density of material, and the material will stretch for maximum length and able to withstand load given to it. It can withstand more amount of load. Okay. In general, material which has large pore size tends to more elastic. It can withstand more strength. Okay, when you are going for a higher temperature, the pore diameter is getting decreased, but it won't withstand more strength. The elasticity property will get reduced. Okay, able to understand? When you are increasing the temperature, its elasticity behavior reduced, so that that material cannot withstand more amount of load. That's what I'm telling here. So the pore diameter of the sample was measured using a line scale, the same photograph. Okay, the average pore size of the natural bone material is in the range of 632. On heating, the pore is getting reduced. For particularly for 2 degrees centigrade, it's 20 micrometer getting reduced to 612 micrometer. For that, for different temperatures, the pore size are getting reduced. This due to on heating, the strength and the bond length of the hydrogen bonds in the materials getting decreases. The shrinking could be due to the decrement of bond length of hydrogen bonds. Therefore, the mechanical strength of the material is also reduced due to the shrinking effect in the pores of bone. So the bones at higher temperature cannot withstand maximum amount of load. That's my point. Then UV visible spectroscopy. Since already I am in the running out of time, unable to explain all these basics. Anyway, I can give the brief about this visible spectroscopy study. Yeah, this is the sample equipment. Here we have a sample holder inside of this box, and we are sending the UV radiation, UV visible IR radiation through this source, so that one can able to record. That the recorded spectrum can be visible on the screen on the monitor. So here one can see the different UV absorptions. See at 230, 345, that is for pure one, and there is a slight shift for the another higher temperature, the sintered materials. So anyway, this that is the peak around 239 remains same. This indicates that the OH stretching vibrations. By using this kind of studies, one can able to find out their band gap. Band gap is so 4.6, 4.5, 3.8, 3.7, and 3.4. So when you are increasing the temperature, the band gap getting reduced. But anyway, all these band gaps are under the category of insulating material. So here, yeah. See, all the bone samples, initially we need to dissolve in HCl acid. Why? Because we need to dilute that pore size or the samples. It is like in the particle only, so it won't give proper reliable result. Therefore, we need to dilute it with the use of HCl acid before going for this study. And then we have a vibration. That is a molecular vibration of a PO4 molecule at 230, and on due to effect of heating, it is slightly shifted to some other points. Oh yeah, OH vibrations is at 340 nanometers. Okay, so the vibrations present nearly, that is nearer the range of 340 to 330. It is giving the OH vibration, that is due to the water molecules, and other vibrations in the range from 220 to 240. It is due to the PO4 molecules. Okay, right? Then this is a formula called absorption coefficient. This absorption coefficient will be useful in calculation of energy. Okay, this EG is called band gap energy. We have a calculation so that we have identified the band gap values. All these band gap values are belongs to insulating materials category. So the heating effects play a major role in changing their band gap. That is a physical property getting changed. Okay, so this again we need to reconfirm with the another equipment called Hall effect equipment. So whatever the study, whatever the results we are getting from one study, we need to correlate the same thing with the other studies. That is the real research. Simply I'm getting this results and giving the results is not an efficient manner in science to discuss all the studies and characterization. Okay, anyway, let it be. Here, the Hall effect, we need to have a sample like this rectangular plate. We need to prepare actually. We need to make the sample like this structure. Okay, in one direction, that is the current direction. This is current direction, and in a perpendicular direction, we are applying a magnetic field. Listen carefully. We are sending a current in one direction. We are applying a magnetic field in perpendicular to the current direction. Therefore, the voltage will be developed in a direction perpendicular to both B and I. Let us consider we are sending a current along the x-axis. So there is a development of that is we are sending a magnetic field in the y-axis. Therefore, there will be a development of voltage in the z-axis. Let us consider current is the x-axis, magnetic field is the y-axis, and development of voltage is along the z-axis. So we are not giving any voltage; it is getting developed. The development voltage is called a Hall voltage that can be measured by keeping a voltmeter across the sample as shown in the figure. So by this studies, what are all the information one can able to get it. So this is a setup. See, here in between the this is the magnetic poles. In between the magnetic poles, we need to keep the sample. Okay, and then here we have wire connections and what is the voltage that can be measured by using this simple multimeter setup. Okay, and these are all the connections necessary for finding all these kind of applications in order to find out physical parameters. Okay, so this is the electrical properties what I have been got the result from the system Hall effect. Bulk concentration, mobility, resistance, resistivity, Hall coefficient, magnetoresistance, electrical conductivity, and average Hall coefficient. See, the important parameter is resistance. This resistance, it is 2.9 10 power 9 ohm. In terms of resistivity, it is 1.09 and 10 power 5 ohm centimeter. This is in Siemens. Then magnetoresistance. These two are very important. Okay. Here also, it is understand that the resistance is very high. See, the resistance is 10 power 9. It's in the range of giga ohm. It is very high resistance. So that it is understood that this high resistance related to insulating material category. Okay. So it is confirmed. Okay, ma. So the bone of suitable thickness we need to select for this kind of at the room temperature, and we are applying a suitable current. Therefore, the development of voltage, resistance, and conductivity and all one can able to measure by using this kind of a Hall effect at the room temperature. We have sending the current of 1 nanoampere only, very small current. That to the sample are not withstanding. It is showing maximum resistance. Nearly it is resisting the current with the applied voltage, applied magnetic field of about 0.5 Tesla. So the Hall voltage is found about 1.4 millivolt. For this amount of small current, it is developing 1.4 millivolt. Then carrier concentration, mobility, electric resistivity, so many parameters one can able to identify. Okay, like mobility, resistance, resistivity, Hall coefficient, magnetic resistance, and all. But the important point which I am going to correlate with the UV visible spectroscopy is that it shows the electrical resistivity of about 1.09 10 power 5 ohm. That's electrical, it's very huge. This is in the range of insulating material category. So this insulating behavior of the prepared materials are confirmed by both the studies like UV visible spectroscopy band gap value and electric resistivity value from Hall. Okay, so I'm coming to the conclusion. So in the present case, this is the first time we are reporting the natural bone from the human and analyzed so many physical properties. It is understood that the crystallite size increases when the temperature increases. When the temperature increases, pore size getting reduced. That are all the information can be identified or obtained from the scanning electron microscopy. An optical band gap value and the Hall coefficient value are related with one another. It is showing this insulating material category. So by analyzing these kind of physiochemical properties of human bone, one can able to develop an artificial bones for the better replacement of injured natural bone to the human beings for their long life. Okay. Thank you, students and the faculty members, for giving an excellent opportunity to discuss all my research findings on bones to the students. Thank you all. I'm waiting for the question.
Thank you so much, sir, for your valuable insights on a lot of materials and a lot of information also we gained about this bone and bone factors, how to test the samples, and how far novel is your research work. So all these things we came into a good picture. And thank you so much for your valuable speech. So in this regard, I request the students, if you have any doubts, you can ask. Or you can please raise your hand, I can allow you to talk. Or please post your question in chat box. Sir, I have one question.
Yes, sir. Yes, sir.
Sir, is there any other material apart from hydroxyapatite for bone replacement? So any novel material?
Yeah, but people are working on titanium material. It's a very highly dense material. It's having a higher thermal stability, nearly 2500 degrees centigrade. It's a very high stable material.
Okay.
People are working on titanium-based materials and some alloy materials in order to replace this hydroxyapatite materials. Why? Because this kind of hydroxyapatite materials can withstand the temperature of about 900 degrees centigrade maximum.
Okay.
But the porosity nature and all very good. People are mixing the hydroxyapatite materials with the titanium and other aluminum materials. So many alloy materials are also there. People are trying actually, but it is there. It is there. People are working.
Okay. So
But
since
thing is, we need to
natural,
get a nano sized structure. Nano sized four structures should be there, should be present in the prepared material.
fine, sir, fine, sir. Because naturally we have hydroxyapatite present in our body itself. That is a natural bone. That's what you have commented. And that is what we just want to make sure whether if the bone is replaced with the titanium or some other material, whether the stability and the factors will be correlated with the natural bone material or it will be varying.
Sure.
Right.
But we need to check the compatibility of the material what we are preparing with the patients. It is different from patient to patients. Why? Because for the adults it is more dense. For the aged persons it is light dense. Even they are just skidding while they are running or walking, bone is getting simply cracked. So we need to check the compatibility first. If it is suitable, then we can replace. If it is not suitable, we need to identify the suitable materials. That's the important. So that people are working in variety of materials with the hydroxyapatite materials.
Okay, sir. Okay, thank you. Sir, we have one question from Sherif. We are working on mandibular bone fractures. So can you tell me about rebuild the mandibular bone in artificially? Is it possible? This is what the question
is. It is made up of what materials? Composition, material composition.
So it depends on the material compositions, right?
Yeah, it is depends on material composition. See, the composition is slightly getting different. It may not be suitable. It may not be compatible with the patient. So we need to thoroughly check its compatibility and their stoichiometry ratio. That is very important.
Okay. So I guess Sharif, sir, your question is being answered. Or if you want to ask some more things on your part, you can raise your hand. I will allow you to talk. I think Sharif sir, I've allowed you to talk. If you want to raise a question based on your thing, if it is not answered up to your expectation, you can just unmute yourself and ask, sir. Okay. So is there any other questions from the participant side or from the faculty side?
I'll just ask.
Yes, sir. Please, sir.
Dr. Shiva, is there any nanofibers used for this applications? Bone.
People are mixing this titanium nanoparticles with the hydroxyapatite. They are changing their stoichiometry ratio. Say, for example, in one of my slides, I have shown you some calcium synthesis part. Let me show it. Chemical synthesis. This is the chemical synthesis formula. Actually, we are taking 10 mole percentage of calcium hydroxide, 6 mole percentage of phosphoric acid, hydrogen phosphoric acid. So with this, one can change this calcium part or phosphorus acid part. For example, one can take 8 mole percentage of calcium and 2 mole percentage of titanium particles, titanium nanoparticles. So that one can able to synthesize the titanium based hydroxyapatite materials. Then we need to check the structure. But the thing is, the structure should not change. So you need to add like a dopant to the structure. It should not change the structure. If the structure is getting changed, it won't be compatible for the patients. Yeah, people are doing. Yeah, there.
Okay.
Yes, sir. Thank you, sir. Thank you for answering. And I have one
Yeah.
question. So,
Yeah.
can you please give some insights about bone cement, which is used for bone grafting techniques? Normally, in this bone cement, bone cement.
cement. Okay. But actually, I'm working on natural bone only, not
Okay.
going for any artificial preparation. Since
Okay.
this is the first, we need to check its natural physical part. Then only we can go for artificial things. But I'm concentrating only this kind of natural bones. So we are working on this artificial preparation of hydroxyapatite. But I don't have much idea about the cementing. But we are in the preparation level. We are preparing the materials for the industrialist. They are having their own way for their different engineering parts of medical application. But cement,
Okay,
I
sir.
don't have any idea.
Okay, sir. Okay, sir. Thank you. Because in artificial bone emulation, I've actually read somewhere in research article like they're using bone cements. So that could
Yeah,
be
yeah,
a
it is there.
supplement for this hydroxyapatite, like just interlinking the bones with respect to the natural and artificial. So that's what I've just heard about. So I just want to make some insight about. That's what I've asked this.
Okay.
Okay. No problem, sir. So is there any other questions from the participant side or from the faculty side? Yes, I guess all the questions have been answered. Sir, shall we wind off, sir?
Yes, Prabha. It was a nice talk, Dr. Shiva. It was really good. And we'll also looking forward to collaborate with you. Look into some
definitely.
of collaborating.
Yeah.
And
this is a very unique work. No one is doing this kind of a natural bones because ethical committee is very important. They are not allowing.
Yes.
But we tried our level best. We are working on it. So it's a very unique work. I'm also welcoming your collaboration.
Sure. And I think there is another question from Aishwarya, Prabha.
Just a minute. Yeah, just now only she has posted. Yeah. Sir, can I ask the question, sir?
Yeah, please.
Okay. What are all the methods to synthesize artificial bone through nanocrystals?
To my knowledge, I can say only the chemical route. Because this chemical route one can able to change the stoichiometry ratio. When you are going for any special methods, if you are for example, ultrasonication method is there and a microwave radiation method, the radiation should not affect the chemical structure or crystal structure. If it is not affecting, then you can go. But up to my knowledge, I can suggest this chemical route synthesis method. Why? Because one can externally modify the synthesis chemicals, change the composition like micro to nano level, ppm range, one can able to change. In order to avoid the radiation's effect, it is okay. A chemical route method is suggested method.
Yeah, okay, sir. Thank you. I hope, Aishwarya, your question is being answered. So is there any other questions? So before winding off, we'll just want to just put up a last comment. Like if you have any other questions, you can put it in chat box so that we'll have a discussion. Yeah. Sir, one more question from Aishwarya. Does nanocrystal help in detecting kidney-related problems?
No. It won't affect your kidneys and all. This is a highly dense material, and at the same time, we have more covalent bonds. It is interrelated with each other. Therefore, we have a long chain process. It won't get break. It won't affect the kidney-related problems. It won't give any kidney-related problems. No.
No, actually, she is asking about does nanocrystal help in detecting kidney-related problems?
I don't have much knowledge because we are in the preparation and then we are not the deduction part. We are analyzing and we are helping the industries to prepare the this kind of nano bio-based nano crystals, hydroxyapatite crystals. I don't think so. This nano crystals, yeah, it may deduct in finding the kidney related problems, but we need to check its diagnostic applications first. How it is compatible with the blood flow, so that one can able to identify their reduction level. Yeah, it is there. It is possible, but we are not working on it. Yeah, up to my knowledge, it is possible only. You can able to deduct the kidney related problem by using this kind of nanometers. Since it is in the range of nanometers, it is possible.
Fine, sir. Fine, sir. Thank you. Thank you so much for all your answers. Yes, sir, I think it is time for us to wind off. Sir, shall we wind off, sir?
Yes, Prabha, we can wind up.
Yes, madam. Santoshini ma'am, you can formally wind off.
Okay, sir. As an end comment, I would like to sincerely thank our management for permitting us to conduct this webinar. And I would like to thank our today's speaker, Dr. N. Shivakumar, for sharing the valuable insights about advanced developments in synthesis of bio-nano crystals. And thank you, sir. I would like to thank our HOD for his support extended towards this webinar session. And I would like to thank our fellow faculty members for their wonderful coordination. And finally, I would like to wholeheartedly thank all the participants from different locations for making your presence and making this webinar a success. Once again, thank you all. Thank you.
Thank you. Thank you so much, Sivakumar sir and HOD sir.
Prabhakar sir. Yeah, thank you. Thank you, Ravindran sir.
Thank you very much, Shiva. It was actually nice. Every time we request you, you are actually making yourself free to give a talk for us. Thank you.
Okay. Yes, thank you.
Thank you, sir.
Thank you, sir. Thank you, Prabhakar sir. Okay.
Thank you, sir. Thank you so much.
Yeah.
I'm ending up the meeting.
Yes.